Well, you are listening to the Advanced Refrigeration Podcast. Here with your hosts, Kevin Cook and Brett Wetzel. Today, we're going to talk about different types of regulating. Kevin, you want to take the lead?
Sure. So we're going to start out with EPRs or inlet pressure regulators. So the purpose for using a EPR in an application would be to control a certain evaporator temperature or pressure to keep a certain space or product or box at a certain temp using the pressure temperature relationship of a refrigerant. So in order to do this, we use a inlet pressure regulator. So we are holding back pressure in order to keep that food or product or process at a certain temperature. So we have several different types of EPRs. We're going to go over Sporlan ones specifically. We have pilot-driven EPRs. We have internal driven EPRs. And we have electronically driven EPRs using a stepper motor to control temperature. So we'll start off by going over the external piloted EPRs. Sporlan offers the Sort 12, the Sort 15, and the Sort 20. They use a hot gas pilot supply in order to operate the valve. When the pilot line is open, the valve is operating under pilot supply. So it's shoot, I messed that up. When the valve is open to the pilot line, it is operating the valve via the pressure setting. So it's taking hot gas and it's driving the piston up and down. The pressure setting is set to. When this valve is energized, it closes off the pilot solenoid so it no longer bleeds to the suction line. And then the valve shuts and stops all flow. So it is a EPR. It is a positive shutoff. It has a solenoid coil. If it is a non-solenoid coil sort valve, and it is just going to maintain pressure. If the pilot line is closed off, it's going to open wide up. So it is no longer going to go off of what the pressure setting is for diaphragm. It's only going to open wide up to whatever the common suction pressure is.
Having that line shut off will also cause the valve, even if the solenoid de-energizes, not to shut all the way. It'll keep flow through it all the time.
Correct. It'll flow 100%. And if you were to try to pump down a system, you would have to shut that valve off in order to pump down the system, or else it's going to take forever to pump.
A lot of times it's just easier just to shut down the pilot line and try to pump it up that way. It's not regulating.
Correct. So, Brett, you want to take the internal piloted valves?
So you have the Sporlan Pi valves. They do not have a cast iron body. They'll have a brass body. There is no externally piloted line on there. It actually uses the pressure to help assist flows, as well as to help regulate. There's no hot gas line that has to be ran, so they're nice if you have to run them all the way out to a case. Works exactly the same way as the Sport 12 or 15 as far as the adjustment on the diaphragm. But like we said before, there's no externally pilot to assist it closed or assist it to regulate. They do have the option on those particular valves to have more than one solenoid on them. Typically the way it runs with one solenoid, it'll regulate all the time when the solenoid is energized. As soon as the solenoid de-energizes, it'll shut down the EPR and just stop flow entirely to help assist the suction pressure to go up to help with defrost. And when they have a second solenoid, they have the option where if you energize the other solenoid while the other one is energized, it'll actually open up all the way. So they're very common with dual temp function. basically explains the pie valves.
One really important thing with the pie valves is they do regulate very well if they are not sized almost perfectly. If they are slightly oversized, they seem to hunt a lot and not hold their setting.
Okay. Some of the other valves that we use for inlet pressure regulators, basically EPRs, are the bipolar step motors. They're driven by a 12 to 18 volt DC. There's a set sequence that it will power each line coming from either a CPC multiplex board or a Danfoss EPR board. Orland makes some drivers as well. Those are typically, in most supermarket function, they're regulating off of average temperature of the case temperature, and as the average gets down to whatever the case set point would be, they start to close down in order to maintain a certain temperature going across. Now, it's not actually looking in most function, they're not really checking out exactly what the pressure is. Sometimes that function can be utilized with a case controller because it actually has a suction pressure that it's regulating all the time. Those in exact way, where as it closes down, it's raising the pressure, which is obviously raising the saturated inside oil, which is going to raise the discharge air. Those valves, they're pretty reliable. You just have more electronics to potentially fail, unfortunately. If a transformer is not tapped properly, where you're not getting proper voltage, whatever board might be driving it, it's not going to work properly. So checking the transformer that powers those valve drivers is extremely important. Making sure all the connections are actually good from wherever the driver board is all the way to the valve imperative. If not, it might miss a step. And that's basically why a lot of times they overdrive valves to ensure that they're 100% closed. So for instance, to say a CVS 7 has 2,500 steps, they're going to overdrive that typically 10%, which is 250 extra steps just to ensure that you get a full closure on there in case the controller maybe missed a step or two. Anything you want to add?
It's just important when you're troubleshooting these valves and setting them up originally that you really pay attention to what your step rate is. Some of them might be 2,500, some of them might be 6,384, some of them might be upwards. Some Danfoss ones are in the thousands, higher thousand rates. So it also depends on what your actual steps per second is too. Some valves are 150, some are 200. So that all plays into part. Brett was saying about losing the steps. I mean, if it's not set up properly, you're going to have issues in the end. And one other thing to add with those valves is since they open wide up after defrost, typically they're set to average temperature. Sometimes that causes problems with newer high efficiency cases, and it allows the coils to frost over right post defrost. So some of those valves, you may have to limit the pull down percentage so that way you don't frost over coils and or cause the rack to flood out from any liquid sitting in the suction line when those valves open wide up right away. Like a typical EPR where you would have some pressure drop there still.
All right. Some of the other inlet pressure regulators, since we covered the gambit on all the EPR stuff, is a inlet pressure regulator for the utilization of controlling your head pressure and your condenser pressure. Gavin, you want to start this one off?
So we have typically supermarket application or a single application. We have what is considered a droplet voltback valve or an ORI valve. So open on rise of inlet. So we're going to start with what we typically see, and that is going to be a valve, the Parker valve. It's an internally piloted valve. So this valve is basically the most robust and easily changeable valve to do whatever we need it to do. It could be an inlet pressure regulator, an outlet pressure regulator, a differential pressure regulator. So however you set it up. So in this application, we're going to be setting it up as a straight inlet pressure regulator. So what it is doing is going to be on the outlet of your condenser line. So it is going to back up pressure and liquid in your condenser until it fills the condenser up with enough liquid to essentially make the condenser smaller by backing up liquid. and then thus allowing your discharge pressure to increase. So this valve is internally piloted, so it has a large diaphragm inside of it and spring and a piston inside of it. So as you crank down on that adjustment, it increases that spring tension. As it increases that spring tension, it's going to increase the force it needs to lift up on that diaphragm in order to put gas on top of that piston in order to push down the valve and open. So this valve is extremely reliable. You could have it as a electric wide open feature. This valve works in conjunction with an outlet pressure regulator, which we're going to go over that in a little bit. But so some customers use a wide open bypass feature on this valve so they can hold their head pressure down lower. So they keep the valve wide open until they get down to a certain parameter, and then de-energize the valve and let it go to operational mode. Meaning when it's de-energized, it's going to be not bypassed anymore. So then we have an ORI valve. Typically looks like a pistol grip EPR. So it's a right angle EPR. This is just a valve with a bellows and a spring. As you turn in the spring, it increases tension on the bellows, and as the pressure has to come up, it has to push against the bellows and the spring in order to lift it up and allow gas and liquid to flow out. Does the same exact thing as it's just in a smaller tonnage range. Whereas it can be adapted to just about any tonnage we use.
Sometimes you'll see those valves in parallel where a normal typical 8 might be too big for the application that they're trying to achieve. So they might use 2 smaller valves in parallel. So it's really important when they are doing that. You have to make sure that they are basically set for the same thing, where you'll have more refrigerant being held back in the other, but more flow going through one valve than you will the other.
Correct. I just ran into this the other day on a brand new store startup. We had a couple smaller condensers with valves in parallel, and setting them can be kind of a pain because if you don't get them just right, they're going to be fighting each other. So what I found the best way to do this is to drive them both all the way in and then set the first one and then count the number of turns and set the second one out the same amount of turns.
You'll have the same thing with larger applications where, like I said, the AA can go pretty big as far as line size, but if you have a rack that's huge, you might need 2 of those still 8s in parallel in order to take the whole flow of the leg or drop leg, as you refer to.
Yes. The nice thing about the is the spring tension is set. You could set an AA valve in the middle of summertime. The spring tension for every 1 turn is.
So they also use it's for EPRs as well. And I will say from experience, a pistol grip style, the regular swirling ORI is a lot less accurate than a regular AA valve. We had problems during one store where it would drop too low and the case would get too low, and then it would hunt all over the place. Not that it was sized incorrectly, just the regular Parker AA valve was just way more accurate. But you could see as soon as the valve was changed out, the case temperatures were a lot more even than what it was with the regular swirling ORI.
Yeah, I mean, it's just an overall better valve for control.
All right, some of the other valves that we're going to talk about today, since you already brought it up, is the outlet pressure regulator. You have different styles. Swarland makes a CRO, which is actually a crankcase pressure regulator, but they make them in different ranges. So if you're using it for an actual crankcase pressure regulator, the pressure would be all the way from 0 to maybe 80 pounds. And they also make another version where the full CRO, the pressure range is anywhere from 80 to, I believe, 300. This is still an outlet pressure regulator. Both are still pistol grip style valves. You also have the A9, which is a hot gas bypass valve, which is still an outlet pressure regulator. We use them in conjunction with the holdback that we were referring to before on the drain leg. Typically, if you have a system where the minimum head pressure is set, or let's just say 70 degrees saturated for the holdback valve, the outlet pressure regulator that's connected from the discharge line going into the receiver is set usually maybe about 65 degrees saturated. So then that way, when the pressure usually gets about 15 pounds less than what the discharge pressure gets, because when the holdback valve is starting to hold back, that valve is going to clamp down. Because the outlet of that holdback valve is toward the receiver, that means your receiver pressure is going to drop. So if the receiver pressure drops too low, that receiver pressurization valve will then start pressurizing the receiver to help assist to push that refrigerant out of the receiver. Around that?
Yeah. Typically, that 9 valve is going to be your last line of defense in the cold weather. So, I mean, that valve is critical that it's set properly. If it's set too, then you're gonna push all your liquid out of your condenser, and it could possibly cause issues with high head pressure. If that is injecting gas in the receiver constantly, it'll actually cause vapor. It'll actually cause the receiver to vapor lock and keep the drain leg from draining out into the receiver, and it'll push all of the liquid out of the condenser. Typically, you see this if one of these failed or is set wrong. You'll feel it blowing hot gas in the receiver when it should be when it's up out of set point. And this could cause nuisance low receiver levels also.
I've seen those valves are typically only cut during PM to make sure they're set right for the winter operation. And a lot of times what is, when you have that vapor locking situation that he was referring to, basically your discharge pressure is going to be elevated more so than what it should be. So because guys don't look, or technicians don't look at the valves themselves summertime, a lot of times you miss them. I swore up and down like non-condense was my pressure extremely elevated. And the whole time it was because the receiver pressurization valve was feeding all the time. And like you said before about it becoming vapor locked, the receiver becomes vapor locked when basically the receiver becomes at a higher pressure than your discharge pressure. So basically your discharge pressure cannot push out the liquid that's already at a higher pressure in the receiver. So basically the pressure keeps building up and it snowballs and eventually you end up going off on high head pressure.
Correct. I mean, it ends up looking like a lot of times you end up having receiver levels that are inconsistent and all over the place, and or high head pressure trips, depending on what time of the year it is. I mean, if it's the winter time, you may not get a high pressure trip, but you may get really off the wall low receiver graphs and inconsistent graphs. So this is one thing to pay attention to. And the way to properly set this valve is, if it's really cold out, like it's been in like Chicago, if the holdback's holding back, you could generally just kind of tweak that valve in to maintain your minimum receiver pressure. But generally what you have to do is you have to valve off the outlet of it, hook it up to the valve, and then a hose up to the suction somewhere, and you want to crack it, just barely, just crack it enough where there's some flow through there, and you're going to want to lower the pressure, and you're going to want to drive that valve then to increase the outlet pressure. I mean, you don't want to have the gauge wide open because you're not going to be able to set it properly. You just want to barely crack it, and you want to be able to feed refrigerant in there and just kind of dial it into where it sets. I mean, close your gauge. It shouldn't shoot up instantly. If it shoots up instantly, the valve's probably through, but it's not non-positive shut-off valve, so it's not going to positively shut off flow. It is a steel piston in there, and it will bleed through eventually. So if it bleeds through 30, 40 seconds, I wouldn't be concerned with that. Anything to add, Brett?
Well, since I brought up the crankcase pressure regulator, because it's basically an outlet pressure regulator, I'm going to talk about that for a little bit. Basically what those are is it regulates pressure. case of the compressor. Typically only see them on single systems, rack systems. You're controlling the load by having multiple compressors. You're controlling the head pressure by multiple condenser fans. So as soon as you get a higher load, pick on another compressor, brings the suction pressure down, head increases, brings on a condenser fan, and then you're controlling your load very, very closely. On a single system, after a defrost, because you're dealing with a hot pull down, basically the case is going to be above the temperature that it's supposed to be. Most of these systems are designed for the holding temperature, whatever it's supposed to be holding that product at. That's why, like, when you have a case full of ice cream, it takes forever for that thing to pull down because it wasn't made to refreeze that ice cream. It was made just to maintain that temperature. So on a single system, when a unit goes into defrost, obviously the temperature of the coil has to go up. When the unit comes back on, you're going to have elevated suction pressure, which is going to elevate your head pressure and basically elevate your amperage. Now, if the system was designed on the low end, you might overamp your compressor every single time that you defrost. On a single system, you might be defrosting 3, maybe 4 times a day. Multiply that by 365. That's a lot of time to overamp that compressor, especially severely in the summertime. So what they'll do is you figure out basically what pressure it will run and still maintain the amperage below what the FLA is, the full load amps or the running load amps, just so you don't overamp that compressor every single time the unit goes into defrost. So let's just suction pressure is up to 80 psi after defrost, and it gets down to about 60 pounds, and we're running right at RLA or FLA. So basically, you'd set the valve to only allow 60 pounds of pressure going to the compressor after a defrost, just so it doesn't overamp that particular compressor. We had an instance where we changed out a compressor. Customer really didn't say us anything except for, "Hey, I need this compressor changed out." Then the compressor failed again. And he didn't tell us that this compressor keeps failing. And we found out that the reason why was because it was on a single system, need an outlet pressure regulator, installed one. The compressor's been in since we installed the new one.
Yeah, one other thing to add, like one other application for a crankcase pressure regulator, not per se in a crankcase application, would be on a satellite compressor on a rack. And we have certain satellite compressor that's maintaining a lower saturation temp than the rest of the rack. Maybe like a ultra low ice cream compressor. It's maintaining a lower saturation temp than the rest of the rack. Well, may lose a little bit of load or it goes into defrost. We don't want to shut that compressor off. We want to keep it running pretty much all the time. So what we do is we pipe a crankcase pressure regulator around the header from the high stage header to the low stage header, and we set a minimum suction pressure with that crankcase pressure regulator. So that way we can keep that compressor running all the time and keep the load up on it. So that way it's not cycling on and off 300-400 times a day. And we keep everything running more efficiently that way and smoothly. And it also helps with the main header by taking a little bit of load off of it and keeping that compressor happy and running all. So the ORD is basically a spring-loaded check. So the ORD is diaphragm or a diaphragmatic disc and a spring. So all it's doing is looking at a differential across the valve, wherever it's installed. So from inlet to outlet. Typically you see an ORD valve and a receiver pressurization roll. So it's going to be pressurizing your receiver from your discharge to your receiver pressure. So it's going to be looking at your discharge pressure to your receiver pressure. And if it gets to a set amount difference, whether it's a 10 or a 20 pound spring, however it's ordered, it's going to open up and allow hot gas to flow in there to keep that differential set point. So as your inlet pressure regulator or your holdback valve is backing up liquid into the condenser, we're going to be losing flow to our receiver. So as that happens, we're going to obviously reduce the pressure in the receiver, which we don't want that to happen because we're not going to get good liquid flow to our TXVs. We're not going to keep a set delta P that we need. So in order to achieve that, we have this ORD valve or an outlet pressure regulator to keep that receiver at a certain pressure. So that is basically what an ORD valve is. Typically, you see it as a 20-pound check valve. There's several other applications that could be used in, but typically this is what you see it in. It's usually only in smaller applications. Once you get up into racks, most of the time we end up with the 9 valve, which is what we already talked about, using to pressurize the receiver.
Some of the other check valves, the differential check valves that we use are in other systems as well. We have typically OCV on our oil system on top of reservoir. That's a differential oil check valve. They can be rated for 20, 30. Basically what that's going to do is your compressor is typically going to be at the same pressure, whatever your suction is, for your crankcase. So in order to make sure that we can deliver oil back to the compressor, that pressure of the oil system has to be elevated. Typically, if you have a single header SST, it's going to be piped into the suction header. And basically what that's doing is maintaining a differential between the oil reservoir itself and the suction pressure of the rack. So like I said before, so we can make sure that we are delivering adequate oil to our compressor. Also, we have another differential valve that I can think of right now is the DDR or the OLDR or the LDR.
Okay, so these valves, what Brett just said, DDR, LDR, OLDR, and then BL, all those valves will be used as a defrost differential valve. So for hot gas defrost, we're going to create a differential across whatever we're using to flow hot gas, whether it's hot gas or cool gas, whether it's on the discharge line, liquid line. However, we're trying to create differential for reverse flow for the hot gas or cool gas to flow. So DDR20 is going to be a discharge line. It is normally open, or is it normally closed valve. So when it is energized, it is in pass mode, meaning it's wide open. When it's de-energized, it's in differential mode. So a DDR20 is looking at your discharge inlet pressure to your liquid header / receiver pressure. So it's going to have a line coming off going to your receiver, your liquid header. This valve is going to be making a difference between your liquid header or receiver and your discharge pressure. So in order to set this valve or defrost differential valve, you need to make sure that it is either de-energized or energized, however the valve is supposed to be, and nothing is in defrost when you do it, because you won't be able to get an accurate setting with liquid coming back and discharge gas going out. It'll just hunt all over the place. So you won't be able to get a completely accurate setting as you're trying to do this. So there's an OLDR, which would be normally open valve. So when it's energized, it's in differential. When it's de-energized, it is normally open, meaning it's got full flow. Same set. And then OLDR, DR is the exact terminology, meaning whether it's normally open or normally closed, and OLDR is normally open. LDR is normally closed. So, in circumstance, it's going to be on your liquid line, and it's going to pressure difference from your receiver to the outlet of your receiver. So you got your across that valve is trying to get your receiver pressure higher and your outlet of the receiver. That way you could use liquid differential. The advantages of an OLDR to DDR and an LDR is going to have way more unsteady liquid grafts. So in a DDR, a DDR typically causes your discharge pressure to raise a little more. So you could have issues with compressors in the summertime. Me personally, I would rather have a defrost differential valve than a liquid differential valve. They seem to hold their settings a lot better. And we have Parker BL. B stands for bypass, the same as it would for the holdback valve, and then the L stands for differential mode. So this valve is basically the same as inlet pressure for the holdback valve. It's just with a different cartridge kit for an adapter, and we're making it do differential mode now, and it has a cap tube coming off the side of it to measure your pressure drop across the other side, so that you can set your differential on that valve. Extremely reliable valve. Tend to go up from time to time, but they hold their settings much better than pretty much all the other valves. Right.
Yeah, well, you're talking about setting them with the valve regulate or valve energizer unit. My preference would be to have it regulate when de-energized, just because if the solenoid were to fail, right, at least you'd be able to have that differential for your defrost all the time around. That you'd have basically a higher head pressure or higher liquid pressure, and I prefer that rather than having none of my cases defrost. You're talking about potentially hundreds of doors not going to defrost because of a failure of a component. He is right. The DDR can have, if set too high, yeah, it'll cause higher head pressure issues. Same thing with the OLDR. If set too high, you'll have the liquid receiver will basically, it'll go up and down all over the place. What he was referring to as far as setting it with nothing in defrost, basically, so you're having no flow, whether it be hot gas or cool gas going out of the case. The reason why this is if anyone's ever set a nitrogen regulator, you can set it while it's flowing, and you could have it set for 50 psi. You close off that flow, all of a sudden now the regulator is saying that it's at 75. So if you were to do the same thing while you have flow going through it, you're not going to get an accurate adjustment. And once again, you'll have issues where either the refrigerant is flying way too fast through the coil, not actually getting a good temperature exchange, also causing high head pressure issues if on the discharge line, and also causing wacky liquid level all over it, piped in on your liquid line.
Correct. I mean, as the liquid differential valve, I mean, I tend to not favor that valve just for the fact that I don't want inconsistencies in the liquid level. And I mean, if it does cause issues, it tends to cause cases to starve more during defrost, and it just ends up causing a whole host of other issues. I'd rather deal with it on the discharge side. It seemed to be a little bit more reliable.
People need to say that the cool gas defrost is less likely to cause thermal expansion and contraction because you're not shooting it up with 160 degree discharge gas. You have a more constant liquid temperature all year round. The only problem with that is a lot of times in the EMS system, they'll have a termination temperature set. Let's say they have it set for 70 degrees. Well, because your supply of your cool gas is basically coming off your receiver, which is basically off your drain leg, your drop leg, you might not be getting 70 degree actual liquid going, or I'm sorry, cool gas heading out to your case. Cool gas or your receiver line, your drop leg, your drain leg line might be all the way down to, in the wintertime, it might be down to 40 degrees, it might be down up to 50 degrees. So basically what's going to happen is that case is going to go into defrost. It's going to think that it still has to go into defrost because it hasn't actually reached that temperature. And basically what will happen is your flow will have now increased because there's no restriction of that liquid actually coming back. And basically that valve will start clamping down more, trying to maintain its differential. When it does that, it's going to slam down shut. And because it's on the outlet of your receiver, the receiver level will skyrocket. It's another downfall of having a liquid differential valve for cool gas defrost.
Yep. And then the last application, you tend not to see it so much. I mean, I've been able to do it once or twice so far. I mean, I don't think it's going to get clarity more and more as these valves get more and more prevalent. It is an electronic differential valve. So meaning you're using two transistors, an electronically driven valve like a CDS valve, and you're actually stepping the valve in order to maintain your differential, whether it be on your discharge or your receiver outlet pressure to maintain your differential during defrost. So I have yet to see it other than places that we tried it at. So right now I have two stores that are running, and so far so it just takes a lot of tuning on the back end. So it's basically doing the same thing. It's just using a stepper motor instead of.
What kind of valve are you using? I mean, they have different electronic valves and the SDR. Yes.
So one of them is using a CDS 16, the other one's using a CDS 9. So it's using those in a Emerson E2 in order to step the valve. So it's looking at outlet pressure regulator, and it's calculating in the controller a differential across the valve, and it's calculating the controller off a PID loop, and it's opening and closing that controller during defrost. And then once every day it zeroes, and then finds its home position, and then starts regulating again when called for. When it's not called for, it's 100%.
So I have a question about that, because we talked about not setting setting a regular DVR or an LVR, and the unit isn't in defrost. So how do you actually control that? I mean, if you have it set for 25 psi, how to control the psi, in turn it actually might be higher. So what do you do to accommodate that? Yeah.
With the electronic valve. So what I'm actually doing is, when it's been defrost, it's just regulating off whatever the differential is. So I mean, yeah, it may be kind of hard to set. It may hunt a little bit, but for the most part, it's been pretty steady, honestly. I guess it really just depends on the rack itself, but the rack I'm using it in, the hot gas load is pretty steady coming back. So it seems to
I was
work
just curious if
good.
you'd have to have a lower set point. So like if basically you're trying to maintain 5, would you have to set that controller up for 15 so it wouldn't maintain such a high differential?
So both mine are both to maintain. So it is set to a lower differential. So that may be part of the reason it isn't more of a problem. I mean, we only have both these racks on a mezzanine, and they maybe only have like 15 feet of rise. So we don't have, it's in a warehouse application. So it's not like a typical supermarket where we have cases and they're way lower. We may have more of a differential. These are more on coils. So the load is a little more constant.
Understood. The only other valve that I can think of that we didn't touch on is it's basically an outlet pressure regulator for a LPRV, liquid pressure regulating valve. Typically, they have them on systems that have mechanical expansion valves. The reason why is because your expansion valve actually changes size based off of your liquid temperature as well as the delta P. When I refer to delta P, I'm talking about the liquid pressure versus the suction pressure. The lower the delta P, the smaller the valve appears. The higher the delta P, the bigger the valve appears. Same thing with the liquid temperature. The lower the liquid temperature, bigger the valve appears. Higher the liquid temperature, smaller the valve appears. So the valve could potentially change size throughout versus wintertime versus summertime. So to not have that be a factor, so you're not having to adjust valves every season, a lot of customers, they use a liquid pressure regulating valve. Typically, this is on the outlet of the subcooler. They have them set, if the subcooler is set for 50 degrees liquid, you would have that other valve, the outlet pressure regulator, set for 70 degrees saturated. So if we're talking about 407A, you might be trying to maintain about 148 pounds. The reason for this is to make sure that we have 20 degrees of subcooled liquid at all times. Because what would happen is, right, we have 70 degree liquid that gives us 20 degrees of subcooled liquid. Now, if some odd reason the subcooler would fail, expansion valve doesn't work, sensor, electronic control for the expansion valve would stop working. Basically, our liquid temperatures rise. If that liquid temperature does rise, we're basically coming in would be 95 degrees. That valve is still going to be set for that 70 degrees saturated. So if we go all the way up to degrees. Now we would be basically 25 degrees of superheated vapor. So instead of actually still having liquid, no matter how much liquid you have in there, just because of the way the numbers work out, you're going to end up having vapor. A lot of times in those applications, they end up having a bypass around the liquid pressure regulating valve. So they're monitoring the liquid temperature going out to the cases. So if it's supposed to be set for 50 degrees and it starts going up towards that 70-degree mark, where it'll start turning that liquid into vapor, usually around 65 degrees. It's 65 degrees longer than 2-3 minutes. It'll bypass that liquid pressure regulating valve. So we don't actually create flash gas, because what will happen is people will see that the sight glass is actually flashing and they're like, oh, it's low on gas. They start gassing it up before they realize the receiver level will be all the way up to 100%. And then we have issues. But that valve, that setup is to make sure that we're not changing the load of the expansion valve, or I'm sorry, not changing the load. We're not changing the size of the expansion valve versus summer and winter time. Keeps a more constant flow and prevents unwanted adjustment from technicians that are over adjusting valves in both seasons.
So a couple of things to add about that particular setup that you need to look out for is, so that needs to be set to whatever the customer spec is or whatever the print says. So say if it's 138 pounds, 145, I mean, as you increase the pressure setting on that valve and as you increase the outlet pressure regulating setting, you increase your subcooling going to that circuit. So if it was designed for 10 or 15 or 20 degrees and those valves were all set at that, and you crank that valve open because you see it's at 130 and you think that's way too low, even though it's what it was designed for, you crank it open to 109. All of a sudden, now those valves are getting almost double, triple the amount of subcooling that they were supposed to and they were originally set to. So then that ends up causing valves to overfeed and it ends up causing a bunch of flood back. The other thing is that bypass is opening, closing that Brett mentioned. Like, that's there if the subcooler's not working. So if you've got a subcooler issue and that bypass is opening, closing, that plays a dramatic role on your liquid levels, because now your liquid levels are going to be all over the place because you're going from holding back pressure to not holding back pressure, holding back pressure to not holding back pressure. So I take the receiver from 30-40% and then just flatline to zero. And then you're there looking for nuisance receiver alarms, and really it's because the valves aren't set properly or you have a subcooler issue. So those are two really important things that, like, that valve has to be running for that rack to work properly.
I wasn't going to bring this up, but since we started getting deep into this, having those valves set properly and having the subcooler working is extremely important. It wasn't really a big deal years ago, but now with people trying to save money as far as on installations and things like that, a lot of times your liquid lines are sized for the actual subcooled liquid. Case in point, so if you have a lineup that, let's just say, requires 48,000 BTUs of load, you might need 7/8 liquid at 100-degree liquid. You subcool that liquid down to 50 degrees. Now you can probably feed that same amount of liquid with only utilizing a 5/8 line. So the reason why I bring this up is if our subcooler is not working, where our liquid temperature is way higher than what it was intended for, basically now you've decreased the line size going to all your cases, which would cause multiple cases on multiple loops to start potentially having high temperatures intermittently throughout the system because you're not delivering enough liquid to what it was originally intended for.
Correct. I'm seeing that a lot more and more. I'm seeing customers cut back on their liquid line size where they may have a typical 5/8 branch running out. They're dropping stuff down to 1/2 inch where they can to save a little bit of money on installation. So, I mean, that subcooler working is critical. And then same thing with that outlet pressure regulator. I mean, it'll just play havoc on the rack if that thing's opening and closing or not set properly. I see a lot of guys that just run in there and open it, see a valve running warm, and they think, oh, the outlet pressure regulator is too low, and they open it. Well, then the valve comes down, but there's other issues like a strainer's plugged partially. Once you start regulating that liquid pressure down, I mean, any strainers that are even partially plugged are going to show up. So, I mean, you got to make sure those are clean first before you start blaming the valve for liquid flow
That's one of the
issues.
things I'm constantly teaching guys whenever we're doing training. When we're out at a store, I always tell them to start, look at the case first, see if it's iced up, see what issues there are having with that case. But if you don't have the right liquid pressure, the right liquid temperature, the right suction pressure, you might resolve multiple issues just by going back to the motor room and taking a look at that and getting everything back to the way it should be. A lot of times you'll fix other cases. I had a gentleman call me over the weekend and he was saying, he's like, "Oh, I'm having 30 degrees of superheat on this valve and I can't get it down and I don't know what's wrong. I think the valve's bad." So I was like, "We'll go back into the rack. We'll go and look, see what all the pressures are." Come to find out the VFD was running 100%, dropping his liquid pressure all the way down to 100 PSI. Well, for that particular valve, it ended up causing not to be properly sized. And as soon as we got the VFD working, his valve started feeding. He looked at the temperature of the case, dropped 10 degrees in 5 minutes. It was like, so that's why like I try to tell everyone, look at the rack, make sure everything is working the way it is. Pressure, liquid pressure, subcooler temperature, make sure everything is straight there first before we start blaming stuff out on the floor.
Correct. I mean, I'm a big fan of starting at the rack on a service call, which we can go into more on another one of these podcasts. Actually, starting a service call. Yeah, that's basically 360 over the top view of how these valves work. And eventually, as we progress this, I want to break these down more and more, and have more in-depth talks of how each particular valve works and issues we see with them and how to fix said issues with these valves, and a little bit more training and in-depthly on it.
Yeah, we'll start doing different subjects, ones that are requested, or we're going to be doing different types of service calls, covering, like you said, how to start a service call. A lot of times that's one of the biggest things. We want to do the valves because it is wintertime. We're trying to make sure you guys are educated on basically the function of each one of these valves, to identify what they are, and basically then build off that. So we can talk about how an A8 and an A9 work in conjunction with each other in order to fix head pressure issues, essentially in the wintertime when it's too cold. All right, guys. Thanks for listening.